Now, once it hits 15, you tell me.
Okay, sir.
How many are 13, 12, 13 are there?
14 are there, sir, now.
I think we'll start.
Yes.
So, welcome back.
15 have come, sir.
Oh, so 1 second. Okay, so we set out an ambitious target to cover both gradient descent and logistic regression. The previous class we couldn't do that, but today we will complete logistic regression. So, as you recall, I just titled this as the gateway to machine learning because it's the first, the most important techniques or algorithms or whatever method to approach machine learning problem. Particularly when you have a classification problem. If there is a yes, no, I want to cross the road, I don't want to cross the road, it is a convective range, stratiform range, life and death. Okay, so in all these cases, there is a digital 0 and 1, you'll win the election or lose the election. In all these cases, the output is yes or no type, okay, success or failure. So in that case, we should still be able to do a regression. And so the inputs are all real numbers, but the outputs are all digital, 0 or 1, either or. So we'll have to work our way around, okay, and it's very important, and particularly many applications, okay, for many applications, not only in engineering but also in computer science, image reconstruction, cryptology. So this logistic regression is indeed a gateway to machine learning. So we will just quickly run through the slides in the interest of completeness, and so that people are able to connect to what we did in the last class. So I'll just run through some of the slides of the last class quickly, and then we'll go on to today's topic. So in the linear regression example, we saw that we just took the heights of people and their ages, and then we tried to correlate with the height with the age. The outcome or the variable was numerical, as often it is. But the key question to ask now is what happens if the outcome is not a variable? For example, let us say a weather data set with the attributes of humidity, temperature, and wind speed. Each is describing one aspect of the weather for a day. Okay, that means they are independent. They are independent features or attributes or variables. You cannot get the temperature from the humidity, neither can you get the wind speed from the humidity. Okay, so they're truly independent. But then based on a combination of these, somebody will play an outdoor sport, somebody will not play. So we are looking at a survey of people, many people. What final decision will they take? Okay, whether they'll play or not play. So this is just a contrived example so that we understand what's going on. In such cases, the outcome that we want to predict is a yes, 1 or a no, 0. So the regression problem now turns out to be what is called a classification problem. Okay, so this basically we are looking at what we call a classification problem. I want to put them into classes. So it's a classification. Okay, and a potent tool to accomplish this is logistic regression. For those people who have gone further ahead, who already know we're working on machine learning. So this can also be done by neural network, but the logistic regression is very intuitive. Not only intuitive, it has got a physical basis. You know what is going on. So sometimes the neural network can be thought of as a mumbo jumbo. So what we'll do is we'll do logistic regression, the theory behind it. We'll work out an example so that you're able to connect to what we are trying to say. And then towards the end of the course, the same example, we'll all do it by neural network so that there is complete reinforcement of your learning. Okay, wow, what is that? I keep doing this. Control, oh, all right. That was a good slide anyway. Okay, all right. Okay, so unlike linear regression, we have only two possible values or what computer science people call it as labels for the outcome. Okay, so y is an element of. So they will say that y is an element of. So y is an element of 0 or 1. So while we have continuous values for the input, we can have only two possible values for the output, 0, 0 or 1. Okay, 0 or 1. Okay. So there is a magic function called sigmoid, which will take care of all the nonsense, whatever be the input, and it will return values between 0 and 1. So this is called the sigmoid or logistic function. Okay, also called or sigmoid. So it is basically a shape function. Okay, so x is minus infinity to minus infinity plus infinity. So this will be minus 20, whatever. Okay, this varies between 0 and 1. So you can see that initially it's very sluggish, then there is a sudden growth, then there is an asymptotic saturation. It's also called the learning curve. That's why we frequently people will say it has a stiff learning curve. That means it takes quite some time for you to achieve some learning objectives. No, so this function is given by g of z 1 by 1 plus e to the power of minus z. Okay, so once you have a form of e to the power of minus z, you can take care of all values from minus infinity to plus infinity. Okay, so z can take any value from minus infinity to plus infinity, but the output is always positive, number 1, and it always is between 0 and 1. Now, what is this z? So that z is the variable, so which is riding on the z is the variable on which you want to present this hypothesis. Okay, the hypothesis or the proposal function. In Bayesian learning, you also call it as the proposal. What is your proposal function? G of z or g of z equal to 1 by 1 plus e to the power of minus z. This z is a combination, could be a linear, it could be a non-linear, whatever. For starters, let us say that it is a linear combination of your variables. Okay, z is w1 x1 plus w3 x3. Okay, now the problem is, now let's connect to this problem now. Let's connect to this problem. So let us say this is humidity, this is temperature, this is wind speed. Okay, based on that, so the output function is g of z is people will either play outdoor games or they won't play outdoor game. So these three are your variables which you can collect: humidity, temperature, and wind speed. You can collect over a day, over a season, over various places, whatever. Okay, so you collect all the data. So these are the input variables. So these are nothing but your x1, x2, x3. W0 is just adjustment constant, whatever. So in this case, you've got W0 plus W1 x1 plus W2 x2 plus W3 x3. W0, W1, W2, W3 are as yet unknown. Okay. Now, humidity, temperature, and wind speed, you're making all the values. Values are available. Now, the people's response is also available, either 0 or 1. Now, the funda is we should be able to do something, some magic out of it, so that whenever you give humidity, temperature, and wind speed, you tell me whether they'll play the outdoor sport or they won't play the outdoor sport. So this is a classification problem from real numbers, from variables which are having real values. Tell me only two answers, 0 or 1. So there is, and then where is the data science here? Of course, I've got humidity, temperature, wind speed, as well as people's preferences for playing outdoor sport or not. So I have a large data set. Out of this data set, I'm not just doing data analytics. I'm trying to put a histogram, box plot, have molar plot, all that. I'm not doing that. I'm trying to do predictive analytics. I'm going deeper. I'm trying to make this learning, make a machine learn this, so that the machine, once you input humidity, temperature, and wind speed, the machine will learn based on what it is seeing. So the machine is learning from the experience. What is the experience? The experience that these outcomes are playing or not playing are directly correlated with humidity, temperature, and wind speed. Don't worry about equation. Don't worry about law of conservation of mass, momentum, energy, gravity. Don't worry about this. I've given you a huge data set. Hey, machine, please learn it and tell me tomorrow if this is the humidity, temperature, and wind speed, will that guy or girl play the sport or not play the sport? This is machine learning. Is that okay? Now, how do we approach this problem? Now, there are mental constructs. These are physical variables. Which are physical variables? Of course, humidity, temperature, and wind speed are physical variable. Your decision to do 0 and 1 is human, but that is also quantifiable. It is also measurable. I am giving an outcome of 0 and 1. So only these are tractable. These are what are available. From this, we have to have mental constructs. We have to do a mathematical construct, machine learning construct, whatever you stuff. You do whatever masala you want, whatever masala khichdi, whatever you want. Finally, I'll give humidity, temperature, mean speed. You tell me whether I will play the sport or not. This is the problem before us. All right. So, okay. All right. Okay. Now, this G of Z is the Z or Z is now an artificial quantity. Okay. What am I saying? That artificial quantity, I am giving a proposal that Z can be put a linear combination of the three variables, humidity, temperature, and wind speed. And then it rides on a linear distribution, on a linear function. And the W0, W1, W2, W3 are the weights. I don't know the weights as such. Okay. Now, when I input this Z into the G of Z, the G of Z will return a value 0 to 1. Now, I further hypothesize. If that value of G of Z is greater than 0.5, I will play the outdoor sport. If the value of G of Z is less than 0.5, I will not do the outdoor sport. Is it okay? Now, so this is what we have. Okay. All right. Now, since the hypothesis function outputs values between 0 and 1, one can draw a threshold at 0.5 and say that if the outcome value is greater than 0.5, we put it in class 1. That means that outdoor game will be played. Then the probability is given by P of Y equal to 1. That means it is success equal to HW of X. So that is a proposal function. Otherwise, it goes into class 0. The probability will be P of Y equal to 0 for a given set of X and W. For a given set of X and X are the three values, humidity, temperature, and wind speed, and W are the weights as such unknown. It is still a proposal. What are the values of weights? Hang on, we'll get it from our data. Okay. The total probability in this case, the probability will be given by the joint probability distribution, which is basically the product of the probability of success and the probability of failure. So HW of X to the power of Y into 1 minus HW to the X into 1 minus Y. So this can be checked for asymptotic correctness. When Y equal to -1, the second term will become 1. When Y equal to 1, when Y equal to 0, the first term becomes 1. Therefore, once you put Y equal to 0 and Y equal to 1, it automatically satisfies original conditions. What are the original conditions? Success is HW of X, failure is 1 minus HW of X. So this is done. Okay. Now, when something is digital, success or failure, and we put a criterion of 0.5, it is very similar to tossing of a coin, on which our friend Bernoulli did a lot of experiments. So we know that it is a sequence of Bernoulli trials, heads or tails for coin and whatever. So if P is the probability of success and Q is the probability of failure, then Q and P are orthogonal to each other. That means when Q happens, P cannot happen. When P happens, Q cannot happen. When heads is there, tails will not be there. Life or death, rain or no rain. Okay. There's no fussy this thing there. Okay. Now, Q and 1 minus P can be interchangeably used. Now, we already saw that X of success equal to 1, X of failure equal to 0. I've already done these slides before. That's why I'm going a little fast. There is a typo there. It should be Bernoulli trials. Okay. So we'll correct it and send the PDF. Okay. The probability distribution of X is called the probability mean function. F of X is given by P the X into 1 minus P into 1 minus X. Okay. So that is the probability, which is so where X is 0 or 1. Now the expected value. Now I'll just show only the expected value for the sake of completeness, so that you understand what we are doing. So the expected value, let's say Bernoulli. Okay, so Bernoulli distribution. The f of X is a probability mass function, the PMF. Okay, probability mass function PMF. The f of X is given by P of X into 1 minus P. The power of 1 minus X. We also saw an example. You remember? I saw 5 seeds at a stretch. The probability of germination is 0.8, and it has a hit sequence of 1, 0, 1, 0, 1. So what will be? How do you get the sequence? 0.8 into 0.2 into 0.8. So we did that. Okay. So this is the probability mass function. F of X is given by that. The expected value is mu equal to E of X. Since it is discrete, I don't use the integral. I use the summation. X equal to 0 to 1. Okay. And So you know that it is x of f of x. So sigma 0 and 1, there are no intermediate states in between. So it is either success or failure. So sigma equal to 0 to 1. Sir, how many values should I take the sum? Only two values, 0 and 1. Okay, so this is the expectation. So you can write this. So exactly. So evaluate it at 0 and 1. So this is 0, p to the power of 0. 1 minus p into 1 minus 0 plus 1, p to the power of 1, 1 minus p. So 1. Okay. So you can see that the first term is automatically 0. So this is nothing but this is 1 minus p to the power of 0. So this is nothing but. So mu is nothing but p. So you know that is the expected. So how do you do a common sense check of this? A fair coin, the probability of heads is 0.5. The probability of head is probability of head. Let's say probability of head is 0.5 means the probability of tail is 0.5. So P is 0.5, Q is 0.5. What is the expected value after 100 times tossing? What is the expected value of heads? Means it is to be 0.5. What is the expected value of tail? That is Q. That will also be 0.5. So whatever mathematics we have done is basically confirms what is intuitively apparent to us by way of common sense. Okay. So it's called a sanity check or a common sense check. Okay. All right. So is it fine up to this stage? Okay. So Baki, you tell me how many people are there now? I'm not able to see.
22, sir.
All right. Okay. So shall we proceed?
Yes, sir.
Okay. Okay. So the variance is given by. So the variance is given by. So the variance is given by sigma x equal to 0 to x square f of x. And we can prove that the variance is nothing but equal to p. Okay, these slides are available to you. So we can prove that the variance is equal to pq. The standard deviation is root of this. So it is root of pq. All right. Okay. Now, this example we saw. Let us say that we plant 5 seeds of a particular plant. Let the probability of germination of seeds be 0.8, which we term as success. If the germination of one seed is independent, what will be the probability of getting 10101, where the seeds 1, 3, 5 are success germinated, while 2 and 4 did not. So 1 means 0.8, 0 means 0.2. So the sequence will be condition. So the joint probability will be the multiplication of the individual probabilities. So 1, 0.8, 0 into 0.2, 1 into 0.8 into 0.2, 0. Final one is 0.8. So that will be the answer to the problem. So total probability is given by P into 1 minus P into P into 1 minus P into P. It is 0.02. It's a 1 in 50 chance. So it's a small chance to get that sequence. So this is Jacob Bernoulli. He also figured out that 1 plus 1 by n to the power of n equal to E. Okay. Now, why all this drama is basically our total probability now, if you have a hypothesis. So if humidity, temperature, and wind speed are put into the Z, and that Z is taken on to the hypothesis function, and then that hypothesis function is set a limit of 0.5, it is just like the tossing of a coin, then it will have a probability distribution is exactly what follows a Bernoulli. Okay. So this is basically a logistic function or a logistic regression, which is riding on a Bernoulli distribution. The regression is due to a logistic function. Why the regression? Regression. I want to regress. That means I want to find out what do you want to regress. If it is in this form, what are W0, W1, W2, W3? That is the regression. That is the key. That's what we want to find from the regression. So it is a regression which is riding on what distribution? The Bernoulli. Why is it a Bernoulli? Because it has got success or failure. I will play the sport or I will not play the sport. And I have a lot of data. With that data, I regress the logistic riding on a Bernoulli and find out W0, W1, W2, with which you just tell me the machine learn it. You input X1, X2, X3. I will tell you whether outdoor sport will be played or not. Okay. All right. So we have come to this stage now. All right. So now let us get back to the problem of logistic regression. The total probability is now given by this. Okay. Now let's go to this logistic regression. Okay. So your P of now is the conditional probability P of, so I think it's light, right? P of y. P of y given xw is nothing but hw of x. Okay. The power of y into 1 minus hw of x to the power of 1. Okay. This hw is basically the logistic. Okay. So this is the Bernoulli. So please see the connection between the logistic and Bernoulli. That when y equal to 1, y equal to 0, whether it is satisfied or not, we've already seen it. So we can proceed further. Now, in linear regression, we minimize the sum of the squares of the error of all the data entries. Here in logistic regression, we maximize the likelihood over all the samples. Okay. What do you mean by that? So if you give some combinations of W0, W1, W2, if it is a correct combination, with that, you give X1, X2, X3, find out the Z, put the G of Z, check whether it is greater than 0.5 and say they will play the sport. When you say it is playing the sport and then finally there, actually they did not play the sport, it is a failure. So there is an error. When it is saying playing the sport, there it is sport and there also it says that somebody is really played, there is no error. So you'll find out over 200, 300 trials or thousands of trials, what will be the best combination of W0, W1, W2, W3 that will give the closest agreement between the sigmoid riding on a Bernoulli with respect to the observations. So this is what we are trying to approach this problem mathematically. Okay. So in logistic regression, we maximize the likelihood over all samples. Okay. In LSR, least square regression also, I proved that the sum of the least squares minimization is nothing but the maximization of the maximum likelihood. Okay, maximizing the probability of likelihood. So that's what I'm saying. In actuality, the LSR was itself ML is simplified. We saw this earlier. For simplicity, the log is now converted to probability is converted to a log. Okay, and now there are two things which have been done here. It is done over many trials. So now you can see that P dash of y x of w is given like this. Okay, let's say this is P dash of. Let's say that is P dash. Now this P of w is nothing but sigma equal to I equal to 1 to m. M is the samples. Okay, HW of xi to the power of 1 minus 1 minus HW of xi, you can put xi to the power of 1 minus 1. Okay, right? So this is for one case. Now for over all the data points, it is W is a vector. W is W of W0, W1, W2. So you can call it as the feature vector or whatever. Goal is to get this. Goal is to get W0, W1. Okay, that is our goal. Okay, now what we do is PW is maximized. Okay, since it is a nonlinear function, it cannot be directly maximized. What we do is we approach it numerically, but before we approach it numerically, we convert it into a ln of PW. Okay, so the ln of PW equal to L of W equal to sigma I equal to 1 to M. If you do that, so what you get is Y plus is it okay? Please correspondingly check what I'm writing on the board and as well as whatever is given on the slide. Okay. I'm doing this impromptu, so there may be some minor mistakes. So please try to see the concordance between what I'm writing and I'm writing out so that you get a better feel, you understand it better. Okay. But all the material is contained in the slides. Okay. So y of that log can be converted to ln. So this is what we. Okay. Now, suppose you don't want any of the math. You've got a high power computer. What you can do is you can take 20 values of W1, 20 values of W2, 20 values of W3, 20 values of W4. Okay. So this is 400 into 400. Okay. 16 into 10 to the, if you do 16 into 10 to the power of 4 times. Okay. You generate 16 into 10 to the power of times combinations of W0, W1, W2, W3. Put them on into this, put them on into your logistic function, increase the, raise the probability, blah, 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 and finally find out what is the probability. And then you can plot the probability and find out wherever it is the highest, that is the solution to the problem. Then your gradient descent, whatever we are doing later on in this part of the, in the next 45 minutes of the class, will no longer be relevant. So that approach is called computational statistics. Okay. So in that case, what you do is, so for example, you can say that I plot, so you have to plot what is called a marginal posterior density. So I will do P of y given x, W0, W1, W2, let us say, and now I will plot versus W3. Okay. Suppose I hit a curve like this. So this is the correct value of W3 plus. Similarly, I can plot marginal probability of x, W0, W1, W3. I can plot versus W2. So I may get a value of W2 like this. So this way, you work out the posterior probability density function. Okay. So this is also called the likelihood function. So this is called the marginal. Why it's marginal? Because it's a vector. So it's a 2-dimensional plot. I can take only one of the weights as the abscissa. Okay. So if you do this, then whatever whatever mathematics we are doing later on is not at all required. Okay. Suppose it is too tedious for you to do this. What you can do is you can generate a small number of solutions, and then you can write this on an artificial neural network. The artificial neural network can help you generate this posterior. That is also another machine learning approach to solve this problem. So there are aspects. So for example, you want to go to place A to place B. There can be several ways of doing that. Like this, there could be several ways of solving the problem. So I taught you many concepts today. What is computational statistics? Computational statistics is heavy use of statistics. You just work out all the distribution. So when you take a lot of data and generate something like this, it is called statistics. But when you say something, when you do this, this is probability. So from probability, you go to statistics. When you write, and when you do a lot of this, you work out all this statistics. So this is called computational statistics. Now, at what values of W1, W2, W3, you will take what values of W2? So these are called sampling techniques. A very powerful technique is called the Latin hypercube sampling. So please refer the Google it up. So this will tell you what are the optimum number of samples, in this case of W0, W1, W2, W3, which will give you a good posterior density. Then if you choose this one, X2, X0, X3 are all satisfied, then the subsequent slides are not required for you. But in many cases, either the statistics is too difficult to work out, but also the neural network appears to be like a mumbo jumbo. So since logistic regression is very mathematically correct and is mathematically elegant, we will proceed further. Nevertheless, because there is a log y of this thing and there is a ln here, since there is a ln, it is not possible to directly get like the least square regression, dou s by dou a equal to 0, dou s by dou b equal to, therefore a equal to n sigma xi ya minus n sigma x, or all those nice closed form mathematical expressions for the constants of the regression will not be obtained, Therefore, we'll have to approach it. So we have to approach it numerically. What do you mean by approach it numerically? Rather, we have to approach it iteratively. What do you mean by iteratively? Start assuming values of W0, W1, W2, W3, have a learning rate alpha, and proceed in the direction of maximum rate of decrease of the error or the maximum rate of increase of the probability function. This is the gradient descent. Is it okay? Now, this is I've given you the broad contours of how we can solve this problem. So this, whatever Siddhant or philosophy or approach I've taught can be applied to any problem. Okay. So instead of your G of this, proposal function could be your CFD problem. The proposal function could be from glaciology, aerosol, whatever. In this, our proposal function, it was just 1 by 1 plus e to the power of minus z. It could be anything. Okay. For a classification problem, it is useful to have a logistic regression. So that is called the forward model. Okay, the logistic regression or the regression equation is called the forward model. Of course, if you suppose you leave it apart from this, you already have some knowledge about how W1 will behave. How will the humidity change? What is the probability you can give for humidity even before looking at the data? What will be the probability distribution you can give for temperature or whatever, or your X1, X2, X3, or all the weights, probability of all this. Okay, so that will give you a belief. So that will give you a belief or the prior. So you can multiply those distributions, these kinds of graphs or the curves with those priors, and then what you're now doing will be called the Bayesian approach. It's called Bayesian Learning. It's also powerful. So right now I know that 2-3 professors in IISc are giving you advanced courses on Bayesian Learning. Okay, so this is an advanced course. Probably if somebody is interested, you can take this course. I'm sorry, the P of X, the P is for the W. So you can give a prior for W0, W1, W2, W3. That means, do you have any knowledge of what will be the weight, which will be for the P or something? If you know that, you give that weight. If you don't know anything, just give a value of 1. That means there is no subjective. At the same time, there is no informative prior which is available to you. So that's called a neutral prior. So that means you don't weight anything specifically. All right. That means you don't give special importance to certain values of the parameters. All right. Now we can do since there is a log, a direct solution does not exist for the log likelihood. So gradient descent has to be used. So we have to get the partial derivatives first. Okay. So let's take dou by dou of this thing. I erased everything. All right. So let's do this quickly. L of W equals sigma y equal to 1 to m. M is the number of data points. Y ln HW of xi. Okay. Plus 1 minus y ln 1 minus HW of xi. Okay. Now, dou of LW by dou for a particular jth component. Please note that J is W0, W1, W2, W3. That counter is the J. I is the counter of the samples. Okay. So this is nothing but Y. Now you should have Yi, isn't it? Yi into ln is 1 by HW. Okay. Minus 1 minus 1 divided by 1 minus HW. I'm putting too many brackets. Into okay, so let's call it as 1 and 2. All right. So this is what has been written now. Okay, so this is fine. Let's go to the next page. Now there is some tricky mathematics which is there. Now you have to get the dou by W of dou by dou HW of dou. I mean the D of dou W. So which is dou by dou W of G of Z. So where G of Z is a logistic function. So it is dou by dou W of 1 by 1 plus e to the power of minus z. Okay. Into dou Z by dou W. So it's a chain rule. Okay. So this is what we are doing is chain rule. Okay. Now this is okay. So now G dash of Z is nothing but e to the power of minus z plus 1 minus e to the power of minus z whole square. I'm just differentiating this minus 1 by 1 to the power of minus e to the power of minus z square into minus of e to the power of minus b. Minus and minus will get cancelled. So e to the power of minus z by. So now we can add and subtract 1 to this. Okay. So now we can do that. Whatever is given there. So c is equal to 1 by 1 plus e to the power of minus z. Okay, so we can do 1 plus e to the power of minus z minus 1 divided by 1 plus e to the power of minus z. So is it okay? So 1 plus e to the power of minus z, 1 plus e to the power of minus z is 1 plus e to the power of minus z whole square. Minus 1 and plus 1 will get cancelled. So then e to the power of minus z. So I made no mistake so far. Okay. So now, so this is nothing but 1 by 1 plus e to the power of minus z. Okay, into 1 plus e to the power of minus z plus 1 plus e to the power of minus z minus 1 into dou z. Sir, why all this struggle? No, there is beauty. Again, I'm getting minus 1 by 1 plus e to the power of minus z is nothing but g of z. Okay, so finally, it's very simple. It's not as difficult as you think. So g of z is nothing but 1. This is g of z already. G dash of z is nothing but g of z into 1 minus g of z into dou z by dou. That's it. That is what is indicated in orange color. Is it clear so far? Can anybody endorse?
Yes, sir.
All right. Very good. Okay. Now, therefore, it is clear that. So it is clear that dou by dou W of therefore HW of x is nothing but HW of x into 1 minus HW of x into your dou z by dou W. Where z is now given by W0 plus, that is a beauty. Z is given by W0 by W1 x and blah, blah, blah. Because h is a proposal function, HW of x is basically your proposal function on Z, which is a linear combination of the independent variables which are coming into the problem. Now, dou Z by dou Wj is equal to x of j. Okay, because all the other terms, because x is a linear combination, when you differentiate with respect to that particular Wj, all the other terms will become 0. Only that particular term, Wj xj, in that Wj xj, since the derivative with respect to Wj, you'll get the xj which is remaining. Therefore, the dou z plus dou w will become just xj. Okay. All right. Now, if you substitute this, now you can do this dou w by, so the partial of L with respect to the partial of Wj is the sum over all the samples, that yi by the hw of xi minus 1 minus ya divided by 1 minus hw of xi. Already we have seen that. Then the dou z of dou w is now given by h of w into 1 minus h of x. Is that clear? So that's what I've substituted there. Okay. So the last two terms are basically coming from our previous derivation. Now, if you do the math, so in the interest of time, I will just tell what I have done, what we have done, and then you'll be able to understand. Take the denominator hw of x into 1 minus hw of xi. Cross multiply. Okay. So you will get yi into 1 minus hw of xi minus 1 minus yi into hw. Okay. Denominator will be hw into 1 minus hw xi. Please look outside the brackets to the extreme right. That is also hw of xi into 1 minus hw of xi. Both will get cancelled. Therefore, when you cross multiply and simplify, what will happen is first term, the numerator yi gets multiplied by the denominator of the second term. The second term, 1 minus yi, gets multiplied by the denominator of the first term within the big bracket. And the hw of xi gets cancelled because that is the denominator. That is your, what is it called? LCM. I don't know what is it. I forgot. LCM or HCF, whatever it is. hw into 1 minus hw of xi. Now we have got this complicated expression. Now finally, the derivative becomes. Now, again you simplify. Within the bracket, yi minus yi hw minus hw plus yi hw. hw, yi gets cancelled. So to cut a long story short, finally, so you go. Dou LW divided by dou WJ. Nothing but into yi minus hw of xi into xi. Now apply gradient descent. Okay, so Wj of mu, Wj of old, plus or minus, what have we done? Plus alpha 1 by m sigma. That 1 by m is to take care of because you are summing over all samples. So yi hw of xi into. All right. So what you do is assume an initial data vector, initial parameter vector of W0, W1, W2, W3. So the Wj can be anything, W0, W1, W2, W3. So W1 new equal to W1 old plus alpha 0.05 into 1 by 105, let's say 105 samples, sigma 1 to 105, y of I. If you substitute your original value of W0, W1, W2, this thing, what will be the proposal you're getting? That is hw of xi. Yi is the data point, and then xj is that particular for the jth term for the ith value. Now you sum it over all that, you will get the sigma of I equal to 1 to m over 100 samples, divided by 1 by m, multiplied by alpha, and you will move W1 like this. Similarly, move W0, move W2, move W3. Based on this, you find out what is your, based on this, find out what is your L. Okay. So, and just see, watch the L going down steadily with iteration. That means you're proceeding in the right direction. If it is oscillating too much, reduce the value of alpha. If it is proceeding very slowly, increasing the value of alpha. Otherwise, like what I taught in the previous class, you can use the Cauchy's descent, where with each iteration, you can convert it into a one parameter problem in alpha, find out the best value of alpha, and proceed to the next iteration. So finally, when you do all that, you will come to a stage where the L becomes, the difference between L between successive iterations is very small. At that time, you hold on, you freeze. You freeze what? W0, W1, W2, W3. That is the answer to the problem. After that, what do? You please tell me what is the humidity, X1. You tell me what is the temperature, X2. Tell me what is the wind speed, X3. I will tell you, my regression model will tell you whether you will play outer sport or not. Did I get the point across to you? Is it okay? If you go over this material, will you be able to get it? Can somebody?
Yes, sir.
So this is logistic regression. I think now if you can take any book, you'll be able to follow. That's why I say, you have to listen to some professor. It is always, so you'll pick up some points. Then self-learning becomes easier when that push, that initial, otherwise when you take a book, we don't know somebody, they'll all be computer science professors. So the terminology will be different. So I think if I've conveyed that point, that means it is successful. It is this lecture is successful. Let's go now over to now I always have this because I always put myself on the other side of the table. Sir, finally, what is this? All this drama all about? I make it a point to make this slide or this point in all my classes. So, sir, what is this? Okay, what is all this? Jamila. Okay, boss, hold on. If there are three variables that decide an output, and the output is only yes or no, over and above this, I've got a big data set previously based on these three variables, whether Janta have said, I mean, Janta means people, sorry, IIT lingo, Junta, okay. Janta have said yes or no. I have a huge data set. I want to model. Okay, so what I'm doing is I want to have a model. What model? Logistic regression model. Okay. How do you build the logistic regression model? I construct a logistic regression model riding on a Bernoulli distribution because unfortunately, the right side, the output is a digital. I will either play or I will not play. So I am stuck. It is not a regular regression, which I have been taught from childhood. How to find the average height, this thing, all that and all that. Now I got a digital. Therefore, the logistic regression rides on a Bernoulli distribution, not a Gaussian distribution. And then I use a gradient descent to crack it. Suppose I don't like all of this. I can go to computational statistics. I can work out the statistics. Then you're a complete statistician. Use sampling techniques and all. If you put your beliefs, you quantify your beliefs and put it, that is a Bayesian method. So you can choose a pure statistical approach. You can use a Bayesian approach, or you can do a gradient descent and optimization approach. So optimization is not the only way to solve the problem. So we actually optimized. What did we do? We tried to maximize the likelihood. So we optimized it. So we solved an optimization problem with alpha and all the gradient descent. Instead of optimization, I can work out the statistics. Apart from the statistics, I can make my belief ride on the statistics. That is called Bayesian learning. So if my beliefs are better and better, if I'm an expert, I'm in a better position to solve the problem than a layman. So this is Bayesian learning. So if you're able to combine data with Bayesian learning, with probability, with statistics, that is machine learning. That is machine learning. That's it. Okay. Please note that finally, in this case, I solved an optimization problem. My student Suraj will completely solve it as a statistics problem, which is called the Bayesian method. At the end of the, with belief, that is a Bayesian method. At the end of the day, we have a regression model, which will give a digital output 0 or 1. If three variables, features or attributes are input to the model. As simple as that. It can't get any simpler. As simple as that. Now, let us learn this more clearly from an example in atmospheric science. Okay. So is everybody with me? How many people did I lose out of 22? I don't know. Most of the people still with me? Is it okay?
Yes.
All right. Okay. an example from atmospheric science. Okay, we'll do it in 15 minutes. The problem of, so I've defined the broad problem as the problem of rain classification. Goal: classify the rain as stratiform or convective. Stratiform is generally light rain. Convective is your lot, convective clouds, towering clouds are there, dark cumulonimbus clouds, so which are dangerous, CB. Okay, so my initials, my short form is also CB. So CB is dangerous. Okay, cumulonimbus is a dangerous cloud. Pilots would like to avoid that. Classify rain as stratiform or convective based on radar reflectivity data. Radar, we already talked about this radar instrument. Let's go into the same episode. Varda cyclone hitting Chennai in 2016. Okay. The Global Precipitation Mission GPM classifies the precipitation type as stratiform or convective based on the radar reflectivity at 3 km height, existence of bright band. That means near the 0 degree isotherm, we'll look at something very bright. Why is it bright? Because in the black and white days, it used to be very bright at that time. Now you can see that left picture. There is a 3 to 4 kilometers. There is something. So that is a convective. There is a bright band. So this has been indicated. Now, right of that, there is a larger, higher tower with thick clouds with red color. So they are the convective rain. Okay. Existence. So we are looking at based on radar reflectivity 3 km height, radar reflectivity 8 km height, existence of bright band. So just like the sports playing was humidity, temperature, and wind speed, we are looking at three quantities: reflectivity at 3 km, reflectivity 8 km, and whether bright band is seen or not. What is bright band? Bright band is a peak reflectivity observed at a 0 degree isotherm. 0 degree isotherm, I can get it from this thing or radio sound or whatever. And due to the presence of ice. So this is the major feature of stratiform cloud. Why the big deal about classification is, once I classify, I can have different algorithms for, I can have different regression equations for predicting the rain based on the reflectivity. I can't use a one shoe size fits all the people, would not work. Therefore, first, in fact, I have to go to even better classification. No rain, yes, no rain and yes rain. In yes rain, convective or stratiform. So there should be three. Now we made it simple. It is raining. Once it is raining, either it is convective or it is stratiform. Convective clouds have deep towers. Suppose when you fly in the airplane, if they will say fasten your seat belt, when you're riding a cumulonimbus storm, you can see that it really shakes. So sometimes you can thick dark clouds which exist beyond 8-10 kilometers. Okay, 6-8-10 kilometers. That is a convective cloud. All right. Convective cloud is indicated here. All right. Now, a total of 240 data points are taken from the GPM reflectivity data, same as the event we considered for the Varda. 120 samples are from stratiform or 120 from convective. Flag BB, brightness band. Bright band indicates whether the bright band is observed or not. Based on, so the output, so if the bright band is observed, technically it should be a stratiform rain. Okay. Because it corresponds to 0 degree isotherm. Super cool clouds are not there. So, but sometimes it is not linear. That is why we are using three variables. We are using more features to classify the rain. Instead of just relying on one feature, more features means minimize the risk, minimize the error. Okay. The output is whether the precipitation is stratiform or convective. So look at the footprint, 240 data points, column 1, column 2, reflectivity 3 km, column 3, reflectivity at 8 km, column 4 is basically the bright band, and column 5 is GPM has already classified it as 0 and 1. 0 is stratiform and convective is 1. Okay. Now we are going to machine learn this. We are going to machine learn this using logistic regression. Now the scatter plots show that ideally we should have separate orange, and orange is convective, blue is stratiform. So there should not be a mixing of orange and blue. It should be very clear. But you can see that, go to the extreme right, southeast corner, you can see that there are some orange above. There are also some blue below. So, okay, so it is not very clear. Therefore, we have to use a combination of all these three and put a Bernoulli riding on a logistic riding on a Bernoulli to try to solve the problem. Logistic regression is inevitable. Okay. The three variables in this problem are x1, x2, x3. Reflectivity at 3 km, reflectivity 8 km, and the bright band existence is x3. Since the input data has different dimensions, it is mandatory to normalize. Let's say the highest reflectivity observed was 70. So I divide all the reflectivities by 70 so that I get a value between 0 and 1. X3 poses no problem because it is digital. X3 bright band exists 1. breakband does not exist, it is 0. The data is divided into 2 parts, training and testing. So let's say out of 240 points, we take 200 points for testing. And the last 40 points have not seen this logistic regression. Now we have to ascertain the performance of this logistic regression based on those 40 points, which are not seen by the machine. So it is not learning. So based on this experience, has it learned or has it not learned? That the proof of the pudding is in the eating, as they say. Like that, we have to test it on those samples which were not exposed to this machine. Okay. Procedure. Very simple. Assume arbitrarily some weights, W0, W1, W2, some point not one has been taken. I thank Baki Harish for working out this problem. He's there. He's a PhD, senior PhD scholar. He's an expert in machine learning. Anybody from ISC want to, this thing, he has spent 5 years with me. He's just submitted his PhD thesis. He's having little time now, free time, I hope so. Baki, so I can say that, right?
Sir.
He's an expert in machine learning. He can do Gaussian process regression, machine learning, LSTM, this thing, what have you stuff, right? So he's, so in and out, he knows ML. All right. So if you have some doubt, you can just talk to him. Okay. So on the chat box, Baki, just give your email address as I'm talking.
Sure, sir.
Now it's all right. Okay. Now calculate the linear estimator y hat. So for some particular, let us take the first x1, x2, x3, which are 0.26, 0.210. Riding on this W0, W1, W2, W3, I'm calculating y0. One small number, 0.0014, it has come. Like that, I can do for all the 200 samples, I can calculate the y hat. Okay. This y hat will now go into the logistic regression. Okay. Now calculate the hypothesis. HW of x of I is a vector. HW of x of I is okay. Now 1 by 1 plus e to the power of minus y hat. So previously we calculated as 0.001. Now when you do that, the probability is 0.50. Okay. So since it is more than 0.5, we classify it as yes. So our algorithm will say it is yes to whatever. So like that, you do yes, no for all the 200, and then finally, so this is basically the first few steps. In the same way, calculate the hypothesis for all the samples. Okay. Now calculate the gradient. With all this hard work, we did the gradient. Calculate the gradient for dou W0, dou of dou W1, dou W2, dou W3. All these values have been calculated. These values are given to you. And now evaluate the dou omega of LW is given by 0.01, 0.02, 0.03 and all that. So after this, get the new values of W0, W1, W2, W3. Okay, this I told you how to get it for the circle problem. You remember Cauchy's method. Like that, it's simple. The slides are going to be available to you. So first iteration, we are doing hand calculation. So the new values of W0, W1, W2, W3 are given below. Okay. Now calculate the log likelihood. Now with this, okay, using this formula. Originally it was minus 138. Now it has become minus 136. So it is slightly improved. Okay. Now the reduction is L of old minus L of new whole square. It has some reduction is there. Now you repeat the steps again and again, improve the values of W0, W2, W3 till the L becomes small. The reduction is greater than 10 to the power of minus 6. If it is not happening, repeat the steps 1 to 6. What are these steps 1 to 6? Step 1, initialize the weights with random value. Step 2, calculate the linear estimator. Step 3, calculate the hypothesis. Step 4, calculate the gradient. Then step 5, learning rate. Step 6, calculate the log likelihood and see the reduction. Okay. Now, if you put a table, Baki, you have solved it using Python?
Yes, sir. I solved using Python, sir.
Okay. So we can share the code with them, right?
Yes, sir. I can share.
Okay. So please share the original data set and the code. Anybody who wants to play with that can play. If there is a doubt, they can ask you, right?
Yes, yes, sir. Of course.
Very good. So now at the end of some 2,200 iterations, we got all these values and it is converged. Now, at the 2296 iteration, W0, W1, W2, W3 are like this. 7, 14, 6, minus 2. Now, we need to examine the accuracy of the trained model. Now you choose the data, 3 kilometer DBC, 8 kilometer flag, and the original classification for this. 20 samples from the test data are considered. Now, input variables you normalize, divided by 70. Previously, it was 30, 35. Now I'm dividing by 70, 0.4 it will become. Second also becomes 0.2, 0.4. Now flag is 1100. Classification is 00. Okay. Now that classification is what the GPM is giving. Now our classification is based on logistic regression. Now you calculate the y hat based on your formula, and then you calculate your proposal, and you see if it is, since we have required only binary, look at HW of x. If it is less than 0.5, the classification binary is 0. If it is greater than 0.5, it is 1. So look at this. Look at some column 0.76. It is more than 0.5. I put 1. 0.5908. I put it as 0. 0.039. Please note that I'm reading the last but one column, HW of x. Is everybody with me?
Yes, sir.
0.9628 greater than 0. So I am now classifying. There is already a classification available in column 4, which is the original classification. Now with the binary which I am doing, I have to check whether it is working fine or not. Okay. To evaluate this thing. So if the prediction is true, we give a score 1. Otherwise, we give a score 0. Okay. So now this is called the confusion matrix. Okay. Is it in slideshow or? It's in slideshow?
Yes, sir.
All right. Now the confusion matrix is predicted class positive, negative, actual class positive, negative. How many times when the GPM algorithm gave positive, convective, so stratiform, you are saying stratiform. When they are saying stratiform, you are saying convective. When you are saying stratiform, they are saying convective. So this is called the confusion table. Now go to this. Predicted stratiform, was a true stratiform is 8 out of 20 data points. Predicted convective, true convective is 9. False is 2 and 1. Therefore, totally, we are getting a success of 0.85. Okay. So the 4 benchmarks are accuracy, true stratiform, true convective by overall, misclassification, total false by overall, true stratiform by overall stratiform is true stratiform rate, true convective by overall convective is true convective rate. Okay. Now, so what is a big deal? Now, if we have an upward looking radar, a ground radar, we can use this information to classify rain as convective or stratiform based on the 3 attributes of variables with help of logistic and without the logistic regression model. Okay. Because I already trained the logistic regression. Now, if we have a radar which is having the same frequency, then if it's an upward looking radar from based on training from another radar, I can use this rule to classify it convective and stratiform. What do we do with this? Once we do this, we can use different constants A and B in the famous Marshall-Palmer distribution where Z is reflectivity, A and B are constants. I can get the rain rate for separately for convective and stratiform. All right. So this is basically I just saw today. So this is open access paper, for example, using logistic regression of climate change impact on a complex river system. So they have. So I've just highlighted in red to address the risk of unsatisfactory performance in a climate domain. This study proposed the incorporation of logistic regression into a decision-centric framework. They've proved that logistic regression is doing a good job. So you can see just with logistic regression and data set, you're able to publish a paper. So it is as late as 2019. Okay. So I think I've conveyed the message. Welcome to machine learning. So today you're all initiated, all of you are baptized. So we have learned machine learning today. So you know how to solve a classification problem. So I also taught you a little bit of statistics and Bayesian method and so on. So once you know logistic regression, you're almost there. Then we have to, don't think ML is only neural network. Okay. So I hope so. Actually, we can close the course also, but the neural network is very important. So we'll do 3 hours of neural network, which will be a substitute, which is even more exciting compared to logistic regression, because all problems cannot be solved only with logistic regression. Please note that the same problem can be solved in neural network also. The last 3 lectures will be neural network, and the last lecture on April 12th will be how we have used all these techniques. Baki, Harish, and Sandeep, the 2 PhD students in all our work related to atmospheric science, rain and all that, cyclones, monsoons, and so on. So thank you for your attention, and I will stop sharing. All right. Any questions? So was it okay, today's lecture? You're able to get the point? Key points? Okay. So no, you don't have to speak. Any thumbs up also will be do. Okay. All right. Very good. Thank you very much. So I'll sign off. It's time for coffee. All right. So see you around Tuesday 16:30.